In the previous video we talked about vectors, and after we defined what a vector was, we looked at some of the operations that can be applied to vectors. So we looked at how you can add vectors together, we looked at how you can multiply a vector by a scalar, but we never talked about how you can multiply a vector with another vector. And that's because the idea of multiplying two vectors isn't really well defined. There's actually, it turns out, kind of a lot of different ways to quote-unquote multiply vectors together. One of those ways, and arguably the most useful ways, one of the most useful ways is called the dot product. So in a sense you can think of this as a way of multiplying vectors, but it isn't multiplication it's a dangerous term to throw around. It's not multiplication in the traditional sense. So I'm going to put the word multiplication, or multiplying rather, in quotation marks. So this is a way of multiplying two vectors together. So let me give you the definition of a dot product and a quick example of how it can be used, and then we'll go through a few properties and talk about what it actually means. What is this? How can we interpret the result? So here's our definition of the dot product. I'm going to give us two vectors. So if our first vector u is the vector u1 comma u2, and we have a second vector v, which is equal to v1 comma v2. So if these are two vectors, then their dot product, let me spell it correctly, dot product which is sometimes called an inner product in more general cases. I will not use that term in this class. I don't think you'll see it on the homework, but if you're reading other sources, this term may come up. It's sometimes called an inner product. Is denoted by the following. So the way that we denote our dot product is a u and a dot, and then the v. So it's kind of like the dot that you would normally use for multiplication, and it's given by the following. So u dot v is going to be equal to, we could write it this way, u1 v1, sorry, u1 u2 dot v1 v2 is equal to the following, u1 v1 plus u2 v2. So this is what the dot product looks like. What we do when we multiply these together is we take the first entry of the two vectors and we multiply them together. We take the second entries of the two vectors, we multiply them together, and then we add up the two results. And so the end result of this dot product is just a single number. It's a scalar. So just keep that in mind. This is a scalar. And I should mention, I said it's sometimes called an inner product. You may also hear it called a scalar product. So that is another word. Inner product, scalar product, dot product. I will stick to dot product. So let's do just a quick example. See how this works. Let me give you a vector. Here's u, vector 1 comma 2, and v is the vector 3 comma 4. I want us to find u dot v. So what we get when we do u dotted with v is the vector 1, 2 dotted with the vector 3, 4. We multiply the first components, so the first component of the first vector is a 1, the first component of the second vector is 3, so 1 times 3, and to that I add the product of the second components of the vectors, so 2, and 4. And so 1 times 3 is 3, 2 times 4 is 8. When I add those two numbers together, we get 8. When I add those numbers together, I get 11. So the result of the dot product of these two vectors is 11. And again, it's a scalar. It's a single number. So keep that in mind. Okay. Before we talk about what this dot product means, let me give you some of the properties that it follows. So how can we manipulate these things in general? So one thing you'll notice is that if I take the dot product u dotted with v, it's the same as doing v dotted with u, because it involves addition and multiplication, both of which are commutative operations. So whether I write this as 1 times 3, as I did here, or if I were to write 3 times 1 because the v vector had come first, 1 times 3 is the same as 3 times 1, and 2 times 4 is the same as 4 times 2. The order wouldn't matter. The dot product is commutative. It's also associative with a scalar multiplication in the sense that I could write, if I have c times u, so c is a scalar, u is a vector, and I dot that with v, that's the same as doing c times u dotted with v, and that's the same as doing u dotted with c times v. So I can associate that constant with any one of the terms. I can associate it with the u, associate it with the v, or I can pull it out and associate it with neither of the two vectors when we do it. There's kind of like a distributive property. So if I've got 3 vectors, I've got maybe u, v, and w. So here is u plus v, and I take the dot product of that with w. That's the same as doing u dotted with w plus v dotted with w. And one other important thing, this goes back to the idea of a magnitude of a vector, which we talked about before. I did, I think, double lines for this. So if I want to think about the magnitude of a vector squared, it turns out I can do that by doing u dotted with itself. Because if you think about it for this, u dotted with itself, I would have u1, u2 dotted with u1, u2, and you get the first two terms times each other, so I would get u1 times itself, so u1 squared, plus the second terms times each other, u2 times u2, or u2 squared. And that's the same as the magnitude of a vector, which is u1 squared plus u2 squared, whole thing square rooted, squared. So the square would undo the square root, and we would get this same result. So this is just saying if you want to find the magnitude of a vector squared, you can dot a vector with itself. So that's kind of the idea here. If you want to look in the book, I think they have proofs of a couple of these, but they're pretty straightforward if you just kind of investigate. I think this example illustrated it well enough. Because the property or the operation of multiplication is commutative, the operation of taking a dot product also winds up to be commutative because it's just built from these already commutative operations. There's a really important theorem that relates this, again, back to trigonometry. And it kind of also goes to the meaning of a dot product. So, in a sense, the dot product's going to tell us how similar two vectors are, in the sense of how similar are the directions that they point. So basically, we're going to be able to tie the concept of a dot product to the angle between two vectors. If that angle is very small, then the vectors would be pointing pretty close to the same direction. If that angle is 90 degrees, they'll be perpendicular to one another. If that angle works out to be 180 degrees, they'll be pointing opposite directions. So that's kind of what I mean. Well, we're going to tie it to this concept. So this is sometimes referred to as the dot product theorem. in a sense, it's almost just a secondary way of defining the dot product. We're going to define it in terms of this angle theta between two vectors. So let me write it out, and we'll look at an example. So if u and v are our two vectors, so there are two vectors with an angle of theta between them. Then it turns out the following is true. When you take the dot product of u and v, it's the same as taking the magnitude of u, the magnitude of v, times the cosine of that angle theta between those two vectors. And to prove this, to justify that this is true, I want to draw a picture, and then I want to use the law of cosine. So we're going to use the law of cosines that we talked about in class back in chapter 6, which says basically if we've got a triangle, so let me draw our scenario here. Here's a vector that I'll call u. And here's a vector that I'm going to put tail to tail with that one that I'm going to call v. And this, let's undo that and try to make this a little cleaner. Here is the third side of this triangle defined by these two vectors. And and this is going to be the angle theta between the two vectors. So I want to define this remaining side over here. If you remember, when we added two vectors, so if this was u and this was v, I could just move this whole vector over and do it tail to tip, and this result was u plus v. And so that's not quite what we have here. I want this side instead, this diagonal, and you may remember from last time that result comes from taking the difference between u and v. So let's just see that real quickly. This side is going to be u minus v. I can write the vector like that. It's going to point, let me just make sure I get this correct. Yes, it's going to be pointing in, let me do it in a different color just to make it clear. This is going to be pointing that direction. That is my u minus v vector. So think about it this way. Here was my u. I'm just going to copy it over here. So this was u. And I'm going to add negative v. So v goes this direction. So negative v is going to look like that. There's my negative v. And the end result is that vector, which is a copy of the red vector that we just drew right there. Hopefully that makes some sense if you followed that. So let me go back and undo all of these. But that's why that remaining side of the triangle is u minus v. And so we've got this triangle, and I want to think about the lengths of the sides. This is the actual vector v. If I just want the magnitude of this, the length of this side of the triangle, it's just the magnitude of v. And similarly, if I just want the length of this side of the triangle, it's the magnitude of u. And similarly for the third side, if I just want the magnitude or the length of the side, it's the magnitude of those. So here's our triangle. And if you remember, law of cosines basically says that if you want to try to figure out basically the lengths of some of the sides of the triangle based on other sides, so remember this was solving triangles, angle side angle, side side angle, all of those cases. Law of cosines was used to find some of those, and it looked like the following. So there was c squared equals a squared plus b squared minus 2ab cosine of the angle large C. And so this was for a generic triangle. Drawing it like this, where this is maybe C and A and B. Those were the sides of the triangle, and the angles here was a capital C, capital A, capital A, and capital B. So again, this is the capital version, and this is the lowercase version over here on the left. Let me draw it a little tinier just so it's very clear. That's the lowercase, the other one's capital. So this formula applies to this picture. Let's just write the equivalent version of it for the picture over here that involves u and v's. And so in this case, this plays the role of side C, theta plays the role of angle C, and u and v, these magnitudes of u and v respectively, play the role of a and b, the lengths of those sides. So all we get out of this, if we apply this to our triangle, gives the following. So the length of side C squared, which is this side, magnitude of u minus v squared, is equal to the sum of the other two sides squared, so u squared plus v squared, the magnitudes of u and v squared, minus 2 magnitude of u, magnitude of v, times the cosine of the angle corresponding to capital C, but that's the angle across opposite from the side C over here. So it's the angle opposite of this, which is what we called theta. So there's our picture. Here's what we're looking at. I need to tie this now to, coming back up here, to the dot product theorem. I'm trying to show that this is true. As part of that, I'm going to need to use this relationship right here, this property that says the magnitude of a vector squared is just that vector dotted with itself. So I'm going to rewrite all of these basically a little bit differently. So for example, this piece on the left, I want to think of that as the vector u minus v dotted with itself, u minus v. And then I want to actually carry out that dot product using our properties of the dot product. So basically I'm going to use like this distributive property, and we'll FOIL this out. So using that distributive property, what this is going to be equal to is we literally just FOIL it the same way we normally would. So it'll be the firsts get dotted, and then I'll do this one times this one, so u dotted with this v, that'll pick up a minus sign. I'll have a v dotted with u, also with a minus sign. U dot v and v dot u are the same because we just said that the dot product is commutative, so let me just start writing these down. We're going to get, the next one will be minus u dotted with v, then we'll get minus v dotted with u, and then the last ones will be the negative v dotted with the negative v, that'll turn to a positive sign, and we get v dotted with itself. So this is what we wound up with from the left hand side, and again those two pieces can combine into a single term, minus 2 u dot v. We've got two of them, so that hence the 2 there. Okay, so that's what that piece looks like. If we look at, if we go basically back and replace this in, so let's rewrite this one more time, so it looks back to some of these terms over here. I want to rewrite all these dot products back into these magnitudes. Here's u dotted with itself, so that's really the magnitude of u squared. I've still got my minus 2u dot v, and then I've also got my plus So let's make it totally clear. This piece became this piece. This piece became this piece. And let's do green. This piece is going to become this last piece, which I'm about to write, which is plus the magnitude of v squared. So we got this by foiling it out. This is this whole piece over here. Let's do one more color. In yellow, that whole piece is our replacement for that whole piece. So what we've got is the following. Just give myself a little more room here. On the left, we've got a magnitude of u squared minus 2u dot v plus the magnitude of v squared, and that's equal to, I'm just copying the right-hand side from right here from the law of cosines. I'm just copying this whole piece down. So magnitude of u squared plus magnitude of v squared minus 2 magnitude u magnitude v cosine of theta. And we will cancel any common terms that show up on both sides. I will divide by -2 on both sides, and what we wind up with is on this side we'll be left with u dotted with v, and on the other side it's equal to, those -2's cancel, and we get magnitude of u, magnitude of v, cosine of theta. So basically we just set up a triangle and solved it using the law of cosines in this particular case. Come on, zoom out. There we go. So there's our result for the dot product theorem. But this is really, really useful because it tells us a relationship that ties the dot product to the angle between those two vectors, which is going to be a really useful thing. So how can we find the angle between two vectors? We can use this to find the angle between vectors. So if I know that u dotted with v is equal to the magnitude of u, magnitude of v, cosine of theta, then I can solve that for theta. I'll divide both sides by those magnitudes, and I'll wind up with cosine of theta is equal to u dot v on top, and we divide it by the magnitude of u times the magnitude of v. And if I want the theta, how do we undo that cosine sitting there? We can undo the cosine with an inverse cosine, and we'll get theta all by itself on the left, and on the right we'll have the inverse cosine of u dot v over magnitude of u, magnitude of v. There's our formula for the angle between two vectors. So for example, if we want to find the angle between those two vectors we did earlier, let's say I want to find angle between, and so it's always going to be the smaller angle that it gives us, the less than 180 degree angle, between the vector 1, 2 and the vector 3, 4. So if I let this guy play the role of u, this guy play the role of v, we can figure out what the angle is between these vectors according to that formula. So all I need to do is figure out our angle theta. It's going to be the inverse cosine of the following. So the first thing I need to do is take their dot product. We did this dot product earlier. You may remember it's 11. So again, let me just go over that real quickly. Multiply the first two numbers together, I get 3. Multiply the second two numbers together, I get 8. And add the results. So 3 plus 8 gives me the 11 that I've got here. For the denominator, I need to individually find the magnitudes of each of these two vectors. So the magnitude of this u is going to be the square root of 1 squared plus 2 squared. And then the magnitude of v is going to be the square root of 3 squared plus 4 squared. And so we will get the inverse cosine of 11 on top. This first one is going to be root 5, and the second one is the square root of 25, which is just going to be 5. And so we will get the angle is going to be the inverse cosine of 11 over 5 root 5. And if you want to try to rationalize that denominator, that's fine. I'm just going to do this on the calculator real quickly and get an approximation of this in degrees. So in degrees, let me make sure my calculator is in degree mode before I do this. It is. Okay. So it's going to be the inverse cosine of 11 divided by 5 root 5. And mine is screwing this up. Come on. Sorry, my calculator is screwing this up here. 5 root 5. Make sure I typed it in correctly. There we go. I got, in this case, I got an answer of about 10.3 degrees. So that looks like my answer there. So that's what the angle looks like. We can maybe sketch it just to verify that this looks like a plausible answer by actually drawing these two vectors. So x, y, 1, 2, 3, 4, 1, 2, 3, 4. Do our little hash marks. The first vector points this direction, 1 in the x direction, 2 in the y direction. So there's my u vector. And the other one goes over 3 and up 4. So it's going to wind up at about this point. Sure enough, there's my v. It looks like a pretty tiny angle. 10.3 degrees seems totally plausible for this angle right there, which is our theta. 10.3 degrees, ballpark. So seems plausible. Okay. So back to the discussion of how this all fits together, why we care about this. One thing that's going to be nice is we can now use this to talk about the concept of orthogonality, which is basically a generalization of the idea of two things being perpendicular. So let me talk to you about orthogonal vectors. So for us in 2D, orthogonal means the same thing as perpendicular. It generalizes. The word orthogonal also makes sense in 3D, 4D, 5D, things that we can't actually visualize and imagine anymore. Orthogonal is a generalization of the idea of what it means to be perpendicular. So for us, orthogonal in 2D just means perpendicular. And perpendicular, so again, this is at least in 2D. Meaning these two things are basically 90 degrees apart. Right? This is the symbol that we often use for perpendicular. So, if two vectors are perpendicular, or I should say, let me use the word that we're supposed to be using, are orthogonal, then the theta, that angle between them, will be equal to 90 degrees, or in radians, that's pi over 2. So, going back to, where is it? going back to the result that we had up here, right here. We've defined the dot product essentially sort of geometrically as involving the magnitudes of the vectors times the cosine of the angle between them. If we have this case down here, orthogonal vectors, where that angle between them is either 90 degrees or pi over 2, what is the cosine of pi over 2? So that's the angle that points straight up. Cosine is the x-coordinate. Cosine of pi over 2 is 0. And so regardless of what the magnitudes of u and v are individually, if I take the dot product of two vectors that are perpendicular, this angle will be pi over 2, and the cosine of pi over 2 will be 0. The whole result will wind up being 0. So what this means is, if two vectors are orthogonal, then that angle theta is 90 degrees or pi over 2, and let me delete the period here and say, and cosine of that theta will be equal to 0. So u dot v, those dot product of those two angles, or those two vectors, sorry, which is magnitude of u, magnitude of v, times the cosine of the angle in between them. You can think of this as a secondary definition of the dot product in addition to that one I first gave you. It's automatically going to be 0. What this means, in short, is two vectors are perpendicular or orthogonal, whichever word they use is fine, if u dot v equals 0. Sorry, not a 0 vector, 0. The other way that this could happen is if one of the two vectors themselves was the 0 vector. So let me just put that in here in parentheses. So assuming that neither u or v is the 0 vector itself. So if you're given two vectors, neither of them are the 0 vector, and you take their dot product and get 0, it means those two vectors are orthogonal. So if I just want to check real quickly, check if the vector 1, 2 and the vector 2, negative 1 are perpendicular. All I need to do is check u dot v. If it's 0, they're perpendicular. If it's any other number, they are not perpendicular. So 1, 2 dotted with 2, negative 1. Multiply the first two terms together, I'll get 1 times 2, which is 2. Then to that I'm going to add the product of the second two numbers, which is 2 times negative 1. And I get 2 minus 2, which is 0. So they are perpendicular. Perpendicular. Let me give you a quick kind of general summary of what this means. And then we can do some more examples. One way to think about what the dot product tells us is the dot product, I said this earlier, but maybe I can clarify this point a little bit now. The dot product gives a sense of how similar the directions of two vectors are. So again, this comes from this definition, u dotted with v being equal to the magnitude of u, magnitude of v, times the cosine of the angle in between them. So let's just look at a couple cases. Here's u, here's v. And in our second case, here's u, and here's v. And in a third case, here's u, and here's v. So let's just think about these cases. Start with this one here, assuming that is indeed a 90-degree angle. What do we know for a fact this dot product's going to be? It's going to be 0. What about over here in this one? Well, in this case, that angle theta right there is clearly an acute angle, less than 90 degrees. And so when I evaluate this formula, u dotted with v is going to involve these two numbers, whatever these lengths are. I don't really care. All that I know is that these magnitudes are both positive numbers. So no matter what, this term right here, that's a positive number. This term right here, it's a positive number. They're lengths. It's impossible for a magnitude, a length, to be negative. And lastly, this piece, if theta's small, so somewhere in that first quadrant, less than 90 degrees, an acute angle. In this case, it's, looks like it's maybe 10, 15 degrees, very small. What is the cosine of that angle? So in the first quadrant, what is the cosine? When this angle's tiny, what is the cosine of a tiny angle? I don't know it exactly unless we knew the exact angle, but in the first quadrant, this piece will be positive, again, in Q1, meaning theta less than pi over 2. And what will the end result be? It'll be positive. Alternatively, over here, when I do u dotted with v, this angle theta is more than pi over 2. It puts us into the second quadrant. And in the second quadrant, in Q2, cosine of theta is negative. And so that's for theta that are greater than pi over 2. And that means this end result will be negative. So basically, if the two vectors point in the same direction-ish, right, if the angle between them is acute, we'll get a positive result when we take the dot product. If they're completely perpendicular, we'll get 0. And if they're more than 90 degrees apart, where in a sense you could think of them as kind of pointing roughly different opposite directions, they're kind of pulling against each other, they aren't fully opposite, it's not actually aiming this way, but they're going in generally different directions, you will get a negative result. So you've kind of got this sliding scale. The dot product will be maximized when these two vectors point the exact same direction, because what is, if these two vectors pointed the same direction, if u and v were the same direction, what would the angle between them be? So let's do this one. If I draw, here's u, and here is also v, pointing the same direction, even if it has a different magnitude, that angle theta is 0. And what is the cosine of 0? It's 1. It's as big as cosine ever gets. So in this case, u dot v would be positive, and it would be its absolute maximum possible value. If you think about it in terms of the other case, so if this is u and there's where they're anchored, and this is v, v now points the opposite direction. Now this angle is now 180 degrees, or pi, and if we look at our formula again, when we plug in an angle of pi here, cosine of pi is -1. It's the smallest that cosine ever gets. So in this case, u dot v would be a negative number, as we said over here, but in fact it would be as negative as possible. So it would be the absolute minimum value that that dot product could ever achieve. So this is kind of our sliding scale. It goes from a large positive number when they point the same direction to a slightly smaller positive number when they point kind of the same direction. It goes down to 0 when they're completely orthogonal, when they point 90 degrees apart. And then it becomes negative once that angle exceeds 90 degrees, all the way to its absolute minimum negative, or however you want to think about that. The most negative it could possibly get comes when they are 180 degrees pulling exactly opposite, or pointing exactly opposite directions. Okay, so with this in mind, I want to move on to the next topic. And then I want to do a couple of examples. So hopefully we've only got maybe another 15 or 20 minutes in this video. I know it's dragging on, but this is our last video ever, so bear with me. What I want to look at is something called the projection. I want to look at the projection of one vector onto another. So this last topic, come on. Okay, we'll live with that. I want to talk about the projection of one vector, u, onto another vector, v. This is kind of an advanced topic. I've got a couple in the homework. It's kind of cool, and it's a really useful idea. So I think the easiest way to start this is by looking at a picture. So if I've got two vectors, here is my vector u, here's my vector v. I want to project the vector u onto v. And by that, I mean I want to basically imagine that the sunshine is up here and directly above, and it's casting the shadow, and I want to see this vector right here. That is the vector on v, where v is kind of like the ground, cast by this other vector u. This is the projection of u onto v. So that's kind of the idea. I've drawn it kind of at an angle. In general, you can kind of always think about reframing it. So forcing v, change your coordinate systems, rotate your piece of paper in a sense until v points straight across, and then whatever direction u is going, we're just looking for the shadow that gets cast down where this is a 90-degree angle. We want the high noon shadow where the sun is directly overhead. That's what we want. So this vector right here, I'll draw it in a new color in this case. That vector right there is going to be the projection. I know I basically just recopied the same picture but that I drew a minute ago, but maybe this one's a little bit more clear, drawing it more horizontally. Okay, so this is the picture that we're going for. I want to find that vector, the one that I just drew in red. So how do we find that? First and foremost, let me just tell you the notation we're going to use. The projection of u onto v, so I don't have to keep writing this out every single time, is given by the following. We're just going to do proj of u with a little tiny v down here. So you can kind of think of it as the u being on the v. So the v is like a little subscript. This is how we will denote the projection of u onto v. And that's this red vector that we've drawn right there. So I want to notice a couple of things about that vector, and we can figure out exactly how this all works. Let me just give myself a little bit of room. So notice a couple of things. Notice that vector points parallel. That is not how I'm doing this. Sorry. It is parallel. That looks right. Parallel to v. Points the same direction as v in this case. Hypothetically, just to come back up here real quickly, it's possible that if my v goes this direction and my u goes this direction, what I'll be doing is casting down the shadow again onto the ground, but this vector may point opposite of V. This would be the projection of U onto V. So either way, it's parallel to V. It just may point kind of the opposite direction, so it may have a negative sign relative to where V is, but it will be parallel to it. Okay, so this is important. I just want to do two things. I want to put together these two pieces. To figure out this vector, we need its magnitude and we need its direction, and we've figured out its direction already. I know the direction that it points. It points the same direction as V. So if I just scale that magnitude down to 1, if I just do a unit vector that points in the direction of V, all I need to do is find the constant that gives me the length of the vector, and I can just multiply that unit vector by that constant. So the point is, we'll create a unit vector in that direction. So basically, our projection of U onto V is going to be equal to something, some constant times V over the magnitude of V. This is now, so this is just some constant, and that constant is equal to whatever the magnitude of this vector is that we're searching for, the magnitude of projection of U onto V. And this piece over here is a unit vector in the direction of V. So that's what we're going for. Here is the vector we're trying to find. I'm going to start off with a unit vector that points parallel to V, and then I'm just going to scale it up by some magnitude C, whatever the length of that vector is. That length is whatever the magnitude of this vector happens to be. So this is how we're going to put it together. I've got my direction part. All I need to do is figure out this magnitude. So how do I figure out that magnitude? That's the last piece that we need to look at. Okay, so let me come back up here, draw a picture, and give myself a little bit more room. Again, here's what we're trying to find. I hate to draw this picture a million times, but it's easier than scrolling up and down a million times. So again, here's U, here's V. I want this distance, C. And let me put the angle there just to make it totally clear. That's a 90-degree angle as well. So there's no doubts. Okay. This angle right here is going to be whatever that theta is. It's the angle between our two vectors. So I want to think about this. If I wanted to look at this triangle that we've drawn here, I can think of the length of this side as just being the magnitude of U. And I've got now a right triangle that I've drawn here where we've got some angle theta, and I've also got this magnitude of U term sitting right here, and I want this remaining piece, this side here that is C, this constant that I want to modify everything by. So if you think about it, what is this C? We have a relationship that we can use our trigonometry right here. If I take the, in this case, cosine of theta, I will get C over the magnitude of U. So cosine of theta equals C, that constant that we're looking for, over the magnitude of U. So this is just SOHCAHTOA, adjacent over hypotenuse relative to this angle theta. So here's the ka part of our SOHCAHTOA. And we can solve for C being equal to the magnitude of U times the cosine of theta. Okay, so this is what we've got. The magnitude of U times the cosine of theta. But recall, most of the time when I give you these vectors, I'm just going to give them to you component-wise. I'll tell you, 1, 2, 3, 4. So just like the ones we did in those previous examples. 1 in the x direction, 2 in the y direction, 3 in the x direction, 4 in the y direction, whatever the case may be. I'm not giving you theta. That's the point. I'm not telling you the angle between it. But we have a formula to figure out the angle between them. We just looked at it in the previous part here. The cosine of theta is equal to u dotted with v over the magnitude of u times the magnitude of v. So this formula right here, oops, whatever, that formula we derived way back up, further, there it is. All right, that formula, so that formula up there is the same as the formula that we're using right here. Okay, so all I need to do is put all of this together. Putting it all together. What we've got is that the projection of u onto v is equal to some constant times v over the magnitude of v, right? This was just what we had written right up here. But now we've figured out that c is equal to the magnitude of u times the cosine of theta, but the magnitude of u times the cosine of theta is the magnitude of u times this big mess. So this is equal to the magnitude of u times that big mess times u dot v over the magnitude of u times the magnitude of v times now v over the magnitude of v. Whew. So we can get a little bit of cancellation. This piece can cancel with this piece. Those are just two numbers. This piece right here, the magnitude of v times itself, I get the magnitude of v squared, which is the same as just v dotted with itself. And I can rewrite this whole mess as u dotted with v on top over v dotted with v, the whole thing times v. This will be a scalar, this will be another scalar, this whole thing will just be some big scalar times the vector v. And this is how we will define the projection of u onto v, putting all those different pieces together. So let me write it in one place so I can circle it and highlight it. Projection of u onto v is u dotted with v over v dotted with itself times v. That's what we need. Whew. Okay, let me do a quick example, and then maybe we can do one or two other examples of applications, and we can be done with this. I want to find the projection of u onto v where u is equal to 7, negative 4, and v is equal to the vector 2, 1. So I know my answer is going to be a vector that's parallel to this. It points the same direction as v. Let me just draw as carefully as I can a picture, and hopefully that picture will allow us to here's my x, here's my y. Hopefully this picture will allow us to get kind of an estimate of what we think the answer is going to look like. So let's see, I need to go up to 7 in this direction, so excuse me. 1, 2, 3, 4, 5, 6, 7. And then what do we need to do in the y direction? I need to go up to at least a height of 1 and down to at least a height of negative 4. Okay, so the vector v is the vector 2, 1, so I go over 2, up 1, that is v. And then the vector u is 7, negative 4, so I need to go out 7 and then down to negative 4. I'm going all the way down to that point way over there. And what I'm trying to do, this is the vector of u. This is sort of our ground, so to speak. Continues off in either direction. And I want to find the shadow. Here's our sun at high noon. So you've got to actually kind of turn this thing upside down, or pictures upside down, and project our u down onto the ground. The shadow is going to go straight down so that that is a 90-degree angle. And this is going to be my result. That is the vector that I'm looking for, the red vector right there. What does it look like that red vector is? Looks pretty close to maybe double the length of v. So something in the ballpark of like 4, 2 is probably going to wind up being our answer. So let's guess that. Maybe 4, 2-ish? We'll see. Okay. Let's actually do the computations now and see what we get. So the projection of u onto v is, as we recall, let me get the formula in the frame. There we go. So I need to do u dotted with v. So 7, negative 4 dotted with 2, 1. Divide that by 2, 1 dotted with itself. All of that times the vector 2, 1. So again, this first part is just going to give me a big constant at the end of the day. So let's go ahead and see what we get. So doing that top dot product, I will do 7 times 2, which is 14. And then I will do negative 4 times 1, which is negative 4. So 14 minus 4 is what I get for that dot product on top. That's going to be 10. And on the bottom, I'll get 2 times 2 plus 1 times 1. So that's going to be 4 plus 1 on the bottom. And again, that's times 2, 1. So we just found the top was 10. The bottom looks like it's 5 times the vector 2, 1. And what is 10 divided by 5? Well, by golly, it is 2. And distributing that 2 through, we do indeed get the vector 4, 2. There is our answer. And indeed, it matches the answer that our picture indicated looked pretty plausible. So that's an example of actually computing one of these projections. It is a really useful property down the line. Something, if you ever take a course in linear algebra, this will be a really important idea. It'll come up a little bit again in calculus and calculus 2, and especially in some of the topics that come up thereafter. Let me do one final example of an application that we can use right off the bat to demonstrate the usefulness of dealing with vectors and dealing with the dot product. And this is a physics concept, the concept of work. So if you take a physics class, you'll learn a bunch of different things, but you learn an actual definition of work, what it means to do physical work. And so in the context of a physics class, work is simply force times a distance. So if you apply a force to something and move it a certain distance, you have applied work to that thing. You've done work on that object, so to speak. So in the case of vectors, so this assumes, when I say force times distance, it assumes that the force is pushing the same direction that you're moving something. So I'm pushing this direction, and we're also moving this. Here's my force pushing this direction, and here is the distance that I have moved it, and they are parallel. And that's what we do when we just think about using a times, is we would forget about these being vectors. We would just think about them being two numbers, and we would multiply them together. But it isn't always true that the force and the direction that something gets moved actually point in the same direction. So the direction of displacement and the direction of the force don't have to be parallel. And we can use vectors to compute the force in those cases, or the work, sorry, in those cases. So in the case where the displacement, so where it actually moves, is a different direction than the force, we use vectors and the dot product to compute work. So for us, if capital F vector is my force vector, and capital D is the displacement vector, so the vector showing basically from where the object started to where it wound up, if those are both true, then we have this definition. The work is just going to be the force dotted with the displacement. That's it. So, for one last quick example, let's do one of these problems. Let's see here. I want to find the work done by gravity. So the force of gravity in moving a 10-pound wagon 50 feet down a ramp at a, let's say, 10-degree declination angle. So basically here is the hypothetical ground. This thing is 10 degrees and our wagon is going this direction 50 feet. And where is gravity pulling? Gravity is pointing straight down at 10 pounds of force. So this is kind of the idea. So if I want to do this, let me clean this up a little bit. Let me move this just so I can complete this all the way over, and this will make it a little easier to see. So there's our 10 pounds. We can get a right triangle out of this, and I want to know what this angle is, because this is the angle that is between the direction of actual displacement. So this direction over here, this is my displacement vector D. It's 50 feet in that direction, and this is the one over here for the force. So here's the magnitude of the D rather, and over here, here's the magnitude of the force acting on it, and they point in those two directions. The displacement vector is along the ramp, and the force vector from gravity points straight down. That's the direction of gravity, and these are the two magnitudes of those two vectors. Okay, so in this case, the work, which is just going to be the force dotted with the displacement, I can use my formulation that says that that's just equal to the magnitude of the force times the magnitude of the displacement times the cosine of the angle in between. So I can use this definition of the dot product which we did earlier, the one that involves the angle between it and the two magnitudes. I already know these two numbers. This is 50 feet. So, no, wrong one. This is 10 pounds. So the force is 10 pounds. The displacement is 50 feet. And I just need to know what the angle theta is. What is this angle theta? Well, I know the three angles in my triangle need to add up to 180 degrees. I've got 90 of them taken care of here, 10 of them here. That's 100 degrees. That leaves this angle to be 80 degrees. And so this must be the cosine of 80 degrees. And so what we get out of this, multiplying those numbers, is the constants out front, 10 times 50. I'll get 500 times the cosine of 80 degrees with units of pound feet. And those are the units of work in this case. If we want an approximation for this, I'll need to know what the cosine of 80 degrees is. That's pretty close to a 90-degree angle. It shouldn't be a big number. It's definitely less than a half here. So let me do that real quickly. What is the cosine of 80 degrees times 500? And the cosine of 80 degrees must have been a little less than 0.2, 0.1 something. And I got out of this whole thing, I guess let me just do that number real quickly, sorry. Yes, so this number wound up being about 0.1736, something like that. And the whole number, multiplying that times 500, wound up being about 86, whatever, 0.8 pound feet of work. So there's our result. This is how we can use the idea of a dot product constructively to compute physics problems. This is the last topic that we needed to cover. This is everything that's going to be fair game for your exam. I will be posting probably another video or two just during when it comes closer to time to actually review for the final exam, but everything that you need to get done should be posted, if not already, then very, very shortly. So good luck. Email me if you run into questions on any of this stuff.